Hey everybody, and welcome back to Calc 3 Online. So the plan for today is actually just to really one main problem, and it's a pretty tough one. It involves cylindrical coordinates and triple integrals and all that. But just to kind of get started, kind of warmed up here, I want to go over just kind of these two quick problems right here. So first, I want to sketch the solid whose volume is given by the following triple integral. So the thing that we're actually going to do today that's really tough is a triple integral that we're going to do like a volume problem with. So this is, again, you want to think of this as really...
Hey, Mr.
All right, so that is like a 1, right? So this really is a volume problem. So I'm going to go actually to these two first. So these are like the polar bounds in r and theta. And, if this is z, x, y, those two bounds, right, say that the radius should be 2, right? So I should be going out to 2. But you can see the angle is only negative pi over 2 to pi over 2. So these two bounds basically imply that, like, this is where an angle of 0 starts. Oops, I don't know why I started there. I started at 2. And so we go like around, that would be pi over 2. And then negative pi over 2 is scooting back there, right? And so that is honestly those two bounds all done. Then it has this z bound, and it says z goes from 0 up to r squared. And, 0, that's not too hard to see. That just means it goes to the, goes down to the xy plane, but then it won't go below it. And then z being less than or equal to x squared plus y squared is basically like a, we've got a structure like this, like a bowl, but we've got the bowl chopped off because of the angle restriction here. And so the volume, the solid that we're basically getting is like from that bowl, we go down to the plane, right? So the weird thing is that the blue part there is kind of like the outer shell, right? And we go up to that, but it's this thing in here. So from everything down inside the red circle and then up to the blue curve bowl shape, right? So that purple thing that I'm trying to shade in there is like the solid. It's kind of weird, but that's what it is. So these two are just two more cylindrical equations, basically, that I just want to make sure you kind of know what they would be. They're actually nice things. So if you're thinking cylindrical coordinates, okay, r squared plus z squared, you can think of as then x squared plus y squared, which is the r squared part, plus z squared equals 4, right? And that, hopefully, you recognize as a sphere of radius 2, right? So it's kind of weird, but that's actually how spheres look in cylindrical coordinates. This thing is kind of weird because r is basically, there's no restrictions. So r is basically, allowed to be part of, this set from like 0 out to infinity, right? And then z is like, just basically any real number at all. You can just let it be anything. There's no restrictions on that. You just have an angle restriction, right? So if you're thinking cylindrical coordinates, right, pi over 6 is like, I'm just going to say it's like right there. I'm going to probably mess up this picture, I feel like. I'm going to say pi over 6 is more like that, because otherwise it's going to blend with my z-axis here. Maybe we'll do colors too. So I'm going to say that is pi over 6, and that's this. So there's actually some debate on this one. Sometimes people want this graph to be a full-on plane, and some people want it to be a half plane. I would argue that r is not non-negative, so we can't go back here, like right in the other direction. we can only go like from the origin out. And so if we fix the angle, we can go from here out for however we want in R that way, right? And then the Z is going to let you scale it up. So what you basically get, the way I see it, is it's a plane, right? And it's a plane that like, trying to make that look more parallel there. But it's a plane that basically, I would call it a half plane. So it's like if you took the ray that's down here in the plane, and then you just let the ray scale like up and down, right? Like it can go below the XY plane as well, so that's fine. So it's kind of just like an infinite sheet. Yeah, but it's like tucked up against the z-axis because of the radius part, okay? There is some debate in math, and it's just kind of how you'd want to define your R coordinate for polar and stuff, but sometimes people would let R be negative, and in that case you just get like a true plane. You don't get like a half plane thing, but it's already infinite, so we're talking about different levels of infinity, which is kind of makes your brain hurt. But that is those two. So the real thing I want to do today is really just this one problem, but it's tough. So the problem I want to do is basically find the volume of the object that is formed by the intersection of 3 cylinders centered on each axis with a radius of 1. Okay, so I'm basically saying you got unit cylinders, right? Like here's one centered on that axis. Here's another one centered on that axis. Here's another one centered on that axis, okay? And I'm talking about the weird shape in here that's formed by the intersection. And it's actually this thing, okay? You can kind of see it right here. It's like a beach ball thing again, but like which we saw in a surface area problem, but like weird. A weird beach ball formed by 3 cylinders, okay? And each of these cylinders has radius 1. I'm actually going to erase this because I don't want it here. So that's what we're doing. And I'm going to do it with triple integrals, and they're cylinders, so it kind of makes sense to do like a cylindrical triple integral problem. So I'm going to need an nope, I want dz dr d theta. So again, this is like a 1. So this thing is a true volume, not a hypervolume. This is a volume of that object, of this object right here. So these things, actually also I was just going to add that they actually have a name in math. Not that this matters really for this problem, but they're called, I think it's Steinmetz surface, or solids maybe, I think is usually what you see. And they, that's STEINMETZ. I know I have a chicken scratch, but there's Steinmetz surfaces, solids of like all different types, but they're basically all built out of intersecting perpendicular cylinders and stuff. But anyways, so the problem really just becomes how are we going to set up the bounds, right? And actually also solving it's not super easy. So just to kind of get some stuff down on paper here, we know that R is going to run from, because we're going to do some polar, cylindrical, same difference, right? R is running from 0 to 1, right? And then what was I going to say? The cylinders, right? The equations of the cylinders are like, they have the structure as like something like x squared plus y squared equals 1, or x squared plus z squared equals 1, right? Or what's the other one? Y squared plus z squared equals 1. And if I flip everything into polar, right? And actually we should say really less than or equal to all these, because we're going to be inside of them. So it's like a solid, right? We want to intersect the solid of those. So basically all of these converted into polar looks like r squared less than or equal to 1, z squared plus r squared cos squared theta less than or equal to 1, z squared plus r squared sine squared theta less than or equal to 1. And to get kind of started on this, okay, we're going to have this thing, you know, is symmetric with the origins, centered at the origin, and our object, like, we can think of it as the same way in like every octant, right? So there's going to be like a few ways we can help to simplify this. And one way is we can do a times by 8, like for each octant, okay? That's going to help us. And we can even do a little bit more, and it's because of some nice symmetries. And I think for that, I'm going to actually think of the plane for a second. So the first, what's the word I'm looking for? The first quadrant, okay, so I'm kind of just thinking of the plane for right now. Just literally thinking of some like functional analysis stuff. If you have like pi over 2, and you have 1 then up here, and you got pi over 4 here, right? So we have that the sine function kind of does that for the from 0 to pi over 2, and then this is sine of just like x, let's say, and then we've got that cosine does that. Okay, these are curves. You know, we know they intersect at pi over 4, and we know that at pi over 2, cosine 0 and sine is 1. And so there's some added symmetry if you think of these kind of functions which are dependent on cosines, right, and sines. So if you look at it, right, between 0 and pi over 4, sine is smaller than cosine, right? So on 0 to pi over 4, that interval, right? Notice that, what am I trying to say? So cosine of x or whatever is bigger than or equal to sine of x. So if I do z squared, well, I think I want these in terms of, so I want to solve these for z, I think, which is probably best. So I'm going to solve both these for z. So 1 would become z is equal to square root 1 minus r squared cosine squared theta. And 2 here, and 2 is z equals square root 1 minus r squared sine squared. So on that interval, right, since cosine is bigger than sine, right, I'm taking away more stuff here, right? So this is smaller than this. So if I use 1 and 2, notice that 1 is basically less than or equal to 2 on that boundary only, right? Again, just because cosine's bigger than sine on this region, right? I'm talking like right in here. Just look at that spot, right? So if I take that away, right, 1 minus a bigger thing is smaller than 1 minus the other guy right there. So I can do another symmetry argument here, and that's what's nice. I can instead, for my angle bound, okay, instead of doing a 0 to pi over 2, right, and then doing like an octant times by 8 thing, I can still do a times by 8. I mean, it's still going to be part of it, but I can also throw in a times by 2 for 0 to pi over 4 instead of 0 to pi over 2, on each in each octant, right? So what I want you to see, and this is why I threw this in, which I think is funny, is a quick integration. This problem can be further simplified by, instead of dealing with like the fact that these things are going to like flip-flop and change, right, at a certain point in this, in each octant, really, right, I can just take the part where I know one is always bigger than the other one and just throw in an extra times by 2. So I have a times by 2 for that, and I have a times by 8 for that other part. So I'm going to need a 16 multiplier in order to get this volume the right way. Whew. So that is probably the hardest part, okay? Now just comes the rest of like the bounds here. So we know, we just talked a lot about the angle. The angle is going to now go 0 to pi over 4, which is much nicer than 0 pi over 2 because they flip-flop there. We do still need the radius to reach out to like 1, right? In this chunk, the radius can get out to 1. So we still have a 0 and a 1 for the radius. And then the z, we talked about how 1 is less than 2, right? This kind of function is less than this. So if I solve that for r or z, that's smaller on this chunk than this one. So for z, right, I just want to let z go from 0 to the square root of 1 minus r squared cos squared theta, right? And if I do that setup, then I should be okay, and I should get the volume of this thing with those multipliers in to account for these two different things. And that's probably well, I don't know. Here I might lie to you. It's definitely one of the harder parts of the problem. Solving this one is not super easy also, but it is, I think, harder to set it up is what I'm going to say. And that's what I'm going to do on the next slide. So this is the setup I got, right? I got a 16 multiplier, 8 times 2, 0 pi over 4, 0, 1, and 0 to the square root of 1 minus r squared cos squared. And so first, dz integral is very nice. I'm just going to throw in the square root, basically, because it's square root minus 0. So I'm going to do 16, 0 to pi over 4, 0 to 1, and then I just have, I'm going to throw this 1r in front. That's part of the, dv. And then I'm just going to use the exponent 1/2, I think. So then I have dr d theta. All right. And, if I'm doing a dr integral, cosine squared of theta is constant, which is kind of nice, right? So I can just look at the r's and kind of blank that out in my head. And I see that this is a nice setup for u sub then, right? So if I let u equal 1 minus r squared cos squared theta, then du, negative du, I guess, over cosine squared theta would equal r dr, right? Yeah, I did that right, I think, in my head. And that's what I have in here, right? And so then I'm going to just kind of swap the problem over to a u integral. Okay, I was just looking at it a little more carefully. I definitely did my derivative wrong. You would have minus 2r cosine squared theta. So I should divide by 2. I need to do that also. So now minus du over 2 cosine squared theta equals r dr. That's good. All right, so if I do my u integral here, I'm gonna take the all this stuff out of the first integral. It's all constant, right? So I can do 16 negative, I guess 16 over 2. So that's a true constant. Then I have 0 pi over 4. Then I have to have a 1 over cosine cosine squared theta there. And then I'm basically going to do integral of u to the half du. Okay. And so then you'll get like a, u to the 3/2 over 3/2, or multiplied by 2/3. So it's actually pretty nice, because if you do multiply by 2/3, right, some 2's are going to cancel eventually. And then 0 pi over 4, this thing. And then we've got u to the 3/2, but u is 1 minus r squared cos squared theta. And then I think I am going to have to also put a little bracket there, right? Because now I'm back in theta. I'm back in R world, right? So R's running 0 to 1. Sorry, I'm thinking out loud a lot here. D theta, just trying not to lose my work there. All right, so if you look at this thing, fairly nice, right? If you evaluate it, you got 1 minus cosine squared theta to the 3/2, and then you'll have a minus 1 minus 0 to the 3/2. So basically you have a 1 minus cosine squared theta to the 3/2 minus a 1, right? And so, we've killed off some of these. So long story short, we got a minus 16/3 in front, 0 to pi over 4. We've got a 1 over cosine squared theta now times a 1 minus cosine squared theta to the 3/2 minus a 1 d theta. Which I think, instead of having it look that way, I'm going to erase this one. And I'm actually going to erase all this. I'm going to write it, I'm going to distribute the cosine squared in. So it isn't too bad, but it's just a lot of things to keep track of. Okay, there we go. That looks a little bit nicer, because now I can start thinking about it as two integrals, right? And I might even want to swap this one, I think, because 1 over cosine squared is just secant squared, right? And secant squared is a nice integral, so I might as well put it in the way you guys are kind of used to it. And here, whoops, let me erase that. We can actually do a little simplification in here, because 1 minus cosine squared is sine squared, right? So the way I'm thinking about this is that's really like sine squared, but sine squared raised to the 3/2, right, is going to kill the square, and then you'll just have the cube left over. So I'm going to do one more simplification here, and I'm actually going to just call that thing, not cosine, don't know why I did that, sine cubed theta, okay? This is actually going to help me do this integral out. So there's a little trick that I kind of think of for this stuff. So if I get something like that, sine cubed, right, is of course sine times sine squared. And sine squared is 1 minus cosine squared. And so then you can think of that as sine theta minus sine theta cosine squared theta. And this is kind of nice because you can remember that this is what's up here, right? And then you can divide cosine into that thing, like into both of these, cosine squared, which is nice because it'll kill this one off entirely, and you'll have an integral of just sine, which is super nice. And then this one, it's actually not so bad either. You'll get like a sine theta over a cosine squared theta, right? So basically, if I use that, I'm going to actually give myself a little more room. This is probably a 2 border if I really did this right. So I'm going to use this kind of trig I don't even know if I'd call an identity. I guess I would. But I'm going to basically give myself a third term, sine theta over cosine squared theta. And then I'm going to have minus sine theta, right? Because this part and this part will cancel in the second one. And then I'll have a minus secant squared theta d theta. Okay. So this is actually nice because this is a really nice integral. This is a really nice integral. And this one you can just u sub, right? Which, you know, is also nice. So I probably am not going to go through all of that. Basically, you know, you'll do your integrals here. You'll get like a tangent, right? I guess I'll write maybe what you get for the next step, and then I'll write the final answer here. So you would have negative 16 thirds. And then if you do that integral, all those integrals out, you'll get 1 over cosine theta plus cosine theta minus a tangent theta, right? And then all of that is running 0 to pi over 4. And if you crank through all that, you should get like basically 8 times 2 minus root 2 as the answer, which is some weird number. Kind of odd, I think, that you don't get a pi somewhere in the answer. A lot of times in these things you get pi somewhere, but there's no pi here. And if you want help with this last step, I'm happy to kind of explain it. But I think this one is pretty neat. It uses a whole bunch of cool tricks. Definitely not easy. Definitely not something I would expect all of you to just be able to do really without any help. But a cool application of like cylindrical coordinates for sure.